Okay, hello everyone. Welcome back to our summer school. And just before we start, I'm just going to put a link in the chat. So Andy and Monica and Miroslav have kindly given us their slides so far. So if you've missed anything in the past couple of days, or you want to review anything, you should see them here, and we'll be updating them, and we're expecting tutors slides shortly as well. So anyway, they're all there at this link. And without further ado, we'll continue with Andy's lecture number 3.
Okay, so thanks all for coming back, sticking with me here. So in the last couple of lectures, we've been talking about n equals 2 supersymmetric field theory in 4 dimensions, and one very specific field theory, n equals 2 supersymmetric Yang-Mills theory with gauge group SU2 and no matter, trivial matter. And what I said is that on the one hand, somehow downstream from this is the Donaldson invariance, Donaldson theory. Let's put maybe a dashed line. And then what I didn't tell you in detail so far, but we'll try to tell you today, is that there's another thing that you can do with n equals 2 super Yang-Mills theory. You can look at its low energy behavior. And then that's going to turn out to be again described by n equals 2 super Yang-Mills theory, but a simpler one where the gauge group is U1 instead of SU2. And let me emphasize that most of the kind of nonlinearity and complication in the theory comes from the fact that the group is SU2. So reducing it to U1 is much better. But there's a price to that. So the matter representation will be either the trivial representation or the one-dimensional complex representation with charge 1. I'll write it like that. And what I mean by that is a slightly funny thing. How can it be both? Well, the picture is that there's this Coulomb branch, which is in this case just a one-dimensional complex manifold, and the effective physics of the theory depends on choosing a point of the Coulomb branch. And at most of the points, there's going to be no matter. It's going to be the trivial matter. And there, this theory is really almost trivial. It's very simple. And then there are going to be these 2 special points where the physics is a little more interesting, and you have the representation. The one-dimensional representation with charge 1. So that's the sort of big picture that I am aiming to describe. Then I guess I should also draw the arrow. So in the same sense as the thing on the left gives rise to Donaldson theory, the thing on the right gives rise to Seiberg-Witten theory. Here I mean what mathematicians call Seiberg-Witten theory. Seiberg-Witten theory of 4 manifolds. And then there's the remarkable miracle to its low energy behavior as far as these observables are concerned. So what you get is the statement that suitably understood theory. On the other hand, Seiberg-Witten theory is much easier, so that's somehow much better. Okay, so that's the broad cartoon picture of the thing I'm trying to explain, in, with a few more details in that picture. But let me say just a little bit more, even if you haven't understood anything that I've said so far. I want to try to give you some sense of what this arrow means, this arrow that says low energy behavior. We'll say a technical statement later, but I think it's good to have the kind of physicists feel for what this arrow is. Because when you say low energy behavior, it sounds like some kind of, it's not the whole theory, it's just some approximation to the theory, it's not that great, what's the big deal? But so let me give you an analogy for the kind of thing that this is. Okay. Suppose you've got like a bathtub. And the bathtub has water in it. And suppose you've got like a fan blowing on it. Oh, this is already a challenge for my art skills. Here's a fan blowing on it. Or maybe you've got like a little boat that you put in it. And you want to calculate, okay, maybe you want to make like a computerized picture of what this thing will look like. So you want to calculate, you're a 3D animator, you want to calculate what the water will do, how the water will respond to this fan or this boat. Okay, and you're a good physicist, you know kind of all the laws of nature. So what would you do? Well, the most obvious thing to do, if you know all the laws of nature, is to say, well, this pond is made of a bunch of protons, neutrons, and electrons, right? Protons, neutrons, and electrons. I draw them like this. Maybe like 10 to the 27 of them. And so what I should do, right, is I should get a real big computer, and I should write down the equations that govern these objects. And then I should just, set up my initial conditions and then have the computer solve the equations and tell me, what's going to happen in the future, right? That would be the most direct thing to do. That's the most fundamental thing to do. That's the thing you do if you really know the laws of physics, right? Okay, so that's what you might call the high energy or the UV description of this system. Now in practice, that's not what you do, right? In practice, we know what you're actually supposed to do. What you're actually supposed to do is write down something called the Navier-Stokes equations. Maybe there's other equations for just a bathtub, but generally, if you want to simulate like a boat moving through water, the equations are the Navier-Stokes equations. Let's have an arrow here, and you're supposed to think that this arrow is perfectly parallel to the arrow that I drew here. The arrow going from the SU2 theory to the U1 theory. The parallel here is to go from this description to a description that's given in terms of the Navier-Stokes equations. So what are the variables in the Navier-Stokes equations? Well, they're totally different. They look nothing like the thing you originally had. They involve, some kind of effective velocity, something called the pressure, the density, the viscosity. What even is the viscosity? I've got 10 to the 27 particles. What is the viscosity? But we know from experience that these are the equations which you can actually use if you want to study, a bathtub full of water. Well, to be exact, if you want to study a bathtub full of water and what happens when, a fan hits it, it's probably not the right description to use if you take your bathtub of water and you shoot it with a high intensity laser, right? Or if you throw it into a black hole. So there are some questions for which this description is not appropriate. But for lots of questions, this description is not only appropriate, but it's really the only one you could actually use. And it contains some actual physical insight. You have to have a good idea to go from the left to the right. But once that problem has been solved once and for all, you don't have to solve it again. Every time you have a bathtub of different shape or whatever, you just use the effective description of water, which you've somehow obtained. And you might obtain it by starting with this high energy description. I don't think people do it this way. I mean, I don't think people calculate the density and viscosity of water by starting from a simulation with an enormous number of particles. In principle, you could imagine doing that, I suppose. But once you've somehow determined those parameters, then you're free to use them to solve the problem that you're actually interested in. So this step is a very profound and important step, and that's the step which Seiberg and Witten took in the case of this n = 2 supersymmetric Yang-Mills theory. So this is the hard and important step. So here the solution was in terms of, in the bathtub, the solution is in terms of Navier-Stokes equations. In the SU2 theory, the solution is going to be in terms of this Coulomb branch and a complex integrable system over the Coulomb branch. So this complex integrable system is somehow the analog of the Navier-Stokes equations in this analogy. Okay, maybe I've belabored that enough. But I don't know. So if you don't understand any of the details of this, I want to give you at least some appreciation for what it is that Seiberg and Witten did. So that's in some sense what Seiberg and Witten did. Okay. So I'm imagining you all like in rapt astonishment at this. Fine. So okay, so let's now go back. So last time I talked about considering operators, local operators, in this four-dimensional quantum field theory, n equals 2 to super Yang-Mills. Well, to be precise, what we considered was this thing that we might call the topological ring, which is the kernel of the supercharged Q acting on the local operators mod the image of Q. So I said last time that those operators form a ring and that their correlation functions are somehow particularly nice. And then I said that the Coulomb branch is the spec of this ring. And I guess maybe I was supposed to say max spec of the ring. So anyway, so concretely, what is this ring? So we could formulate this. We could formulate this ring in any n equals 2 theory, in any four-dimensional n equals 2 theory, or even more broadly in other topological field theories as well. Well, in other field theories with a Q operator that squares to 0 as well. Now in n equals 2 super Yang-Mills, with gauge group G. So now for a minute, I'll let G not be just SU2. Then this ring is just the ring of invariant polynomials on the Lie algebra. And it's reasonably so in the classical version of the theory, in the classical field theory, it's easy enough to write down operators corresponding to the invariant polynomials, namely O sub p. So let's call the invariant polynomial p. And by invariant, by the way, I mean G invariant under the adjoint action of G on its Lie algebra. So the operator associated with the G invariant polynomial p, you get by, in the classical field theory, you get by taking the polynomial p and applying it to the field phi. So remember, phi was an adjoint valued field. So locally, it's an element of GC. So phi itself is not a good G invariant local operator. So it wouldn't give you an honest function on the field space as we define the field space, because the field space was the field configurations were considered modulo equivalences. And so a random function of the field will not be invariant under that. But if I take an invariant polynomial, then it is invariant under all the equivalences. So for example, so very concretely, if G is SU2, then R is freely generated by one operator, where P is the operator that, so P is the invariant polynomial that just takes the trace of x squared. So that's an invariant polynomial on Lie algebra SU2. So if G is SUN, then similarly R would be generated by OP2, OP3 up to OPN, where PK of X is the trace of X to the K.
Is there any particular reason why you're taking the second power, even for SU2? What about X to the fourth?
Well, it's determined by the trace of X squared.
So, in terms of, the independent ones.
That's right. That's right. So I'm saying this ring. So I'm saying this ring is the ring of all invariant polynomials. So as you say, I could take trace of X squared. I could take trace of X to the fourth. I could take all kinds of powers. But the ring of invariant polynomials is generated by, for SUN, it's generated by the traces of powers up to X to the n. And
trace of X being 0, so there's nothing there.
That's right. That's right. If I had said UN, then I would have also included trace of X.
Okay, I see. Okay.
Yeah. So for any Lie algebra, this ring is some finitely generated thing with a number of generators equal to the rank of the Lie algebra. Okay, so then in the Coulomb branch, which I introduced last time as the spec of this ring, so B is just is an affine space of dimension n-1. So in other words, we could identify it, at the cost of making some choice. We could identify it literally with c to the n-1. That's what this Coulomb branch actually is in these cases. It's a pretty concrete and simple thing. Okay. And so when n equals 2, B is literally just the complex plane. And I'll let the coordinate on the complex plane be U. So in terms of the expectation values, I would say U is the expectation value of the operator trace of phi squared. That's going to be a function on the Coulomb branch. Okay, now here's what Seiberg-Witten tell you to do. They say, so far what I said, by the way, didn't depend on what, this R, I should say, this is the script R, the chiral ring, topological ring. To be distinguished from the straight R I was using for the matter representation. And what I said so far, I didn't depend on what the matter is, but now I have to actually specialize and say what the matter is. So suppose that the simplest thing, and the one that Seiberg-Witten did first, is the case where the matter representation is just trivial. So I don't have any fields other than the ones that I wrote. So then here's what Seiberg and Witten say to do. They say over this complex plane, consider a family of curves, family of Riemann surfaces. Write them in a different color. So for every U, for every point of the Coulomb branch, I'm going to consider this curve, y squared equals x to the minus 2 times x plus 2u plus x inverse, sitting inside of, so that's a curve sitting inside of C2 parameterized by x and y. And so if you look at them for a minute, you'll see that each one is like a twice punctured torus. Um, and let's equip them with a one form. Holomorphic one form. Lambda equals y dx. And now they say, let's do the following thing. Let's consider, let's let gamma u. So I've got this family of tori. Oh yeah, sorry. Let's say a little bit about what this family looks like. So, so over the Coulomb branch, which is the U plane, now I've got this family of curves, and these curves are smooth. So I said they're twice punctured tori. They're smooth except at u equals plus or minus 1. And so over the Coulomb branch, we have this family of curves, and there's 2 points that are different from the rest, where the curve is singular, and everywhere else the curve is smooth. And let's consider now lattice, which is the first homology of. So I'll compactify the curve by filling in the 2 punctures. The punctures, by the way, you'd think of as in the coordinates I'm writing, you'd think of the punctures as kind of lying over x equals 0 and x equals infinity. So I can fill in over those punctures, then take the homology over over z. So that's as a lattice, that's the lattice z2. Or actually, okay, in fine print, I'm not going to take exactly this lattice. I'm going to take a super lattice of it. But that's a kind of finite index thing, which we shouldn't worry about at first. So roughly speaking, I'm going to take literally the homology of the curve. And then for every lattice vector in gamma u, I'm going to define the period. I'm going to define a number, a complex number, z gamma, which is just the period of this one form around the cycle. Luckily, it doesn't have any residues at the punctures, so so this is well defined just on the homology of the filled-in curve. So now I've got a family of lattices. So at every point of my Coulomb branch, I have a lattice, again, away from u equals plus or minus 1. So they fit together into a local system of lattices. Over, let's call it B prime, is B with plus or minus 1 removed. So it's B with plus or minus 1 removed. But it has monodromy around those singular points, which is given by like the Picard-Lefschetz formula, if you think about what happens at those singular points. Okay, and then now we do the following thing. We say, I want to describe the physics of this quantum field theory locally around some point of this moduli space. So we're going to think of this moduli space as being like the space of possible low energy behaviors of the theory. And we're going to, an interesting thing is we're not going to have a single global description that makes sense everywhere. The first thing you might expect is, you know, as in the story of this bathtub, you might think, well, there's just going to be one uniform low energy description, which is just in terms of, you know, some simple system of equations. And it turns out it's almost like that, but not quite. It's slightly more complicated. And so what you have to do is you first choose a patch. So let's call this patch, say, U. So let's choose a simply connected patch, U and B prime. And now that I'm on a simply connected patch, I can trivialize my local system of lattices. In other words, I've got this torus this torus sigma u, and I can choose a basis now for its homology. Maybe like this. So I'll call this one gamma electric and this one gamma magnetic. So I'll choose a basis, say gamma electric, gamma magnetic for this lattice, for gamma u, for all u and u. I'll do it in a consistent way. So I'll trivialize this local system over over my patch u. So then as it turns out, so now we have these functions. So for every cycle, we have its corresponding period, and now we can consider the periods associated just to our the two basis cycles that we chose. So let's call them A and A dual. So I'll let A be the period associated to gamma electric, and I'll let A dual be the period associated to gamma magnetic. So that's just notation. I'm just calling A and A dual. So now I have two functions, A from U to C and A dual from U to C. They're both holomorphic functions because my system, whatever else you can say about the system of curves, it's holomorphic over, depends holomorphically on U. The one form depends holomorphically on U. So the periods are some local holomorphic functions on U. And in fact, at least if you choose a small enough patch, A gives a local coordinate. So let's assume that A gives an actual local coordinate. So A dual then so we can write the function A dual as a function of A. We've got two holomorphic functions. One of them is like a local coordinate. I can write the other one as a function of the first. So I'll think of A dual now as being a function of A. And now I'll define tau of A to be the derivative, dA dual by dA. Okay, I hope it's clear what we're doing here. So we just started with this, so it was motivated by something in physics, but now you could kind of decouple the physics and just say, all right, this is, this is just some mathematical construction that I do starting with this family of curves. I define, for some reason, I define this quantity tau. Now, here's what Seiberger wouldn't say. They say, suppose I want to compute the correlation functions of the theory, which I called, n equals 2 super Yang-Mills, or I guess I was calling it T of SU2. Sorry, n equals 2 super Yang-Mills, which is the theory T of SU2 and the trivial representation. The first thing Seiberger wouldn't say is that those correlation functions, they first of all depend on a parameter. So this is in the space-time R4. They depend on a parameter U living in the Coulomb branch. So we saw that that's true for the 1-point functions. In fact, the Coulomb branch almost by definition was the set of possible values for the 1-point functions. So the statement is that every possibility is in fact realized by some actual whole system of correlation functions, which when you go back to the 1-point function just recovers the point that you're at. So the theory, the way you would say this more pragmatically as a practicing physicist is that this theory has a kind of degenerate vacuum state. It has lots of different possible vacuum. the analogy is like you have a ball rolling around in some potential, and the potential has degenerate minima. And in fact, classically, in the classical field theory, that's exactly what happens here. You have degenerate minima corresponding to different values of this field phi. Cyrus wouldn't say that's actually also the picture in the quantum theory. And then, okay, fine. Then, for a generic choice of u, or let's say, I can be more precise since we've introduced this B prime. For u and B prime, they are approximately, and I'll try to say what approximately means. They're approximately described by a different theory, simpler theory, T of U1 in trivial. Where now I have to tell you what the gauge coupling will be. So the theory, remember that the supersymmetric Yang-Mills theory depends on a parameter, which is the gauge coupling. So if I say that the low energy effective theory is the Yang-Mills theory with gauge group U1, that by itself doesn't quite tell you what the theory is. To be complete, I have to tell you what the coupling is, and the coupling is this function tau of A. Yeah, sorry, I said U and B prime, but of course I've specialized further to my patch. So I should say just for U and my patch. Once I've chosen my patch, I get a description in terms of the U1 theory, where the coupling depends on the exact point where I am in my patch, and it's given by this function of where I am, tau of A.
But is tau necessarily real?
No. Right, very important. So this tau, I said tau in the first lecture when I introduced tau. I said tau is a complex number, which is the complexified gauge coupling, and I didn't say what that means. So in terms of so you would write it like this, with some 2 pi's or something. I think it's like theta over 2 pi. So in a gauge theory, including in Maxwell theory, there's 2 parts to the coupling. There's what you usually call the gauge coupling, which is a real number, and that's what I'm calling G here. But then there's another piece called the theta angle, and that's what I'm calling theta here. And you put those 2 together and you get a complex number. So I'll write the effective action in a second. And you'll see how this tau enters into the effective action. So in short, tau is not real. It's not supposed to be real. But what you usually call the gauge coupling is the imaginary part of tau.
Is tau related? Is it tau or theta, whatever? Is it related to some sort of anomaly, some sort of singularity, that there is a non-trivial holonomy or something? What is the significance of tau?
What is the significance of tau? So tau,
is it like a flux of something, or
I don't know how to see it as a flux exactly. I mean, so it is the effective gauge coupling. Meaning that are you asking kind of what does it mean to say that it's the gauge coupling, or
no, what you said is basically this is now becoming Maxwell's theory, and in
that's right.
You mentioned that there are 2 couplings.
Right. So I think you're asking what's the theta? What does the theta mean? Yeah. Right. So let me write it. So if you write the action, so the way I wrote it before, okay, give me 1 minute. Let me write the effective action and then come back to this.
Sure.
So a more precise way of saying what I said here is that, so it's effectively described by this theory, but let's actually write what the effective action looks like. So again, I'll restrict to the boson sector. So I won't write the fermions. And then it's an integral. I'm just talking about R4. So I'll write R4 here with the volume measure tau of A times the self-dual part of the curvature. Hang on, I'll write this in a second in a form you'll like better, but tau bar of A bar times the anti-self-dual part of the curvature plus the imaginary part of tau of A times the norm of dA squared plus norm of d squared. So the way we're supposed to think of this, so the effective action is written in terms of fields. So we have now E and little a, where E is a U1 bundle with connection. Oh, and the auxiliary field again. And A is now a, well, I think the best way to think of it is that it's a map from R4 into the Coulomb branch. And we think of it expanded around, so maybe I'll call my base point X naught. We think of expanding it around A naught. So in answer to your question, so one way of answering the question is just to say, look, tau is the thing which appears in the action in this way. But I think probably the more helpful way of saying it is to expand it in terms of the theta and G separately.
Right.
So then the way that G appears is like integral of, it appears with integral of F wedge star F, or this is like the usual F mu nu, F mu nu.
Right.
So that's the usual term that gives you like the dynamics in Maxwell theory. And then there's another term which is purely topological.
Okay. Oh yeah. That
Integral of F wedge F.
Yes. Okay.
So that's the extra part, is this topological term, which would appear here with an I. And so here, that's what we've got, except we've got it with a coupling which itself depends on this scalar. So we've got this scalar that we're kind of expanding around some particular point A naught, and we have a kind of slightly jacked up version of Maxwell theory where the coupling depends a little bit on exactly where you are. And then in the fermionic couplings, you would also see actual derivatives of this tau, which we don't see in the bosons. Okay, so what does approximately described mean? It means that there's a map between the operators O of the original theory and I'll write them OIR of the U1 theory. Now with coupling tau of A naught, such that the correlation function which you originally wanted to compute, so any correlation function which you originally wanted to compute in the SU2 theory, the original SU2 theory, in the vacuum labeled by U, is approximately equal to a correlation function of the infrared version of those operators. So each of the operators of the SU2 theory, when you look at it from the point of view of the U1 theory, becomes some operator of the U1 theory, which I'll call the operator IR. In the vacuum around A naught, where this approximate symbol means up to corrections which decay exponentially in the distances. So the idea is that when you study a correlation function between operators that are very far apart, that then those correlation functions are effectively computed in, more and more accurately in this low energy U1 theory. In other words, everywhere I say low energy, you could equally well think that I'm saying long distance. So the statement is when you want to compute correlation functions at long distance, they're computed by this U1 theory. And so in general, for sort of arbitrary correlation functions, it really is only an approximation. But I told you earlier that there are some correlation functions that are independent of the distances, or said otherwise, they're independent of the metric on the space-time. So you're free in computing them to jack up the metric by an arbitrary amount. And then this approximation gets better and better. In other words, it becomes an exact formula. So that's why this statement is particularly powerful in the for topological correlators. So this statement is particularly powerful. You know, in situations where the correlation function is independent of the xi's. For example, if all the operators are in our chiral ring or their descendants. Or for correlations of descendants on a compact manifold X in the twisted description. Okay. Okay, so what did I tell you? So what I tried to tell you is slightly more precisely what it means to say that this algebraic geometry of this family of curves, the sense in which the algebraic geometry of this family of curves is supposed to capture the behavior of this quantum field theory. Okay. Now, let me just mention one thing, two more things. So one thing you might wonder is, so what I said is I'm giving a description of the physics of this system, or concretely, I'm giving you a way of computing the correlation functions in this quantum field theory. But my description was a little funny. So our description depended on a choice. The choice of a basis for this lattice gamma. So remember, we had this two-dimensional lattice, which was the homology of the spectral curve, the homology of this this curve sigma u. I had to make a choice of a basis, and I called my basis vectors gamma e and gamma m. Maybe I didn't say why, but now I'll explain why they're called gamma e and gamma m. So the first observation is that different choices are really different. So different choices actually make a difference. So if I change the basis by some SL2Z matrix, then I would change my tau, which I said is this physically observable thing. It's the coupling of the low energy theory. I change it to a different tau. So that's like changing the strength of the electromagnetic interaction. We're changing this topological theta angle. So that looks funny. So what's going on? So how can, in short, the puzzle is, how can the same quantum field theory be described both by the U1 theory with coupling tau and by the U1 theory with coupling tau prime? Well, okay, the answer is it's kind of a cool fact that those two theories are actually equivalent. Those two theories are actually equivalent. So that's a phenomenon called electromagnetic duality. So that's a fact about, in fact, that's already a fact about just pure U1 gauge theory. So I'll just say, so this is a true fact about, even if I had just written down the theory with the connection and nothing else, but it also holds in the supersymmetric theory. Okay, so in making this kind of effective description of the physics of n equals 2 supersymmetric Yang-Mills, we found that it is possible to give an effective description in terms of this family of family of curves, but it's not possible to give a single description globally. And the fact that this family of curves has monodromy somehow captures the kind of electromagnetic duality transformations that you have to make when you go from one patch to another in your low energy description. So that's a feature which doesn't occur somehow for this bathtub, but it occurs here. Okay. So concretely, one way of thinking of this lattice gamma is that's the lattice of electromagnetic charges that could be carried by particles or by states in the Hilbert space in the theory, in this low energy effective theory. And that's somehow an invariantly defined thing. And then this choice of a basis, which is something that we somehow impose, choosing a basis, which I call gamma E gamma M, corresponds to choosing which charge will be called electric and which one is magnetic. And so the remarkable thing is that choice is kind of up to you. For any description that I have of a system involving, electrically charged particles interacting with a coupling tau, there's a perfectly dual description of it that someone else could have involving magnetically charged particles interacting with coupling -1 over tau. Okay. So now the last thing, let me at least introduce now the complex integrable system. So once we've come this far, now let's consider. So we have this family of lattices, and we could build a corresponding family of tori. So now compact tori, which in this case might be kind of accidentally isomorphic to the compactified tori that we considered before. But in general, this is the thing you would do. So this is a compact torus, compact 2 torus. And once you pick a basis, as we did above, you could think of it as having coordinates. You could think of it as having coordinates, say theta electric and theta magnetic, within U1 squared. So once we've made this local choice of who's the electric and who's the magnetic particles, we consider a 2 torus, which is just U1 squared with 1 coordinate electric and 1 coordinate magnetic. So these tori fit into a family, which I'll call M. And this M is naturally a complex integrable system, which means I should give you the holomorphic symplectic form. And the holomorphic symplectic form all right, like this. So this A, remember, was a function on the Coulomb branch. And we had A dual, which was also a complex function on the Coulomb branch. And now I'll make this complex 2 form. So now this is on the total space of these tori, total family of these tori. So at every point I have a torus, and I have this holomorphic 2 form, complex, well, it's a complex 2 form on the base, but in fact, this complex 2 form is non-degenerate, so it actually determines a holomorphic symplectic structure. It determines a complex structure and a holomorphic symplectic form. Holomorphic symplectic structure on the total space, M. And this M also extends over the singular fibers. So I gave you a description of it only away from the singularities, but in fact, it also extends over the 2 points where the lattice didn't extend. It extends over the whole B. And that holomorphic symplectic manifold fibered over the Coulomb branch, that's a complex integrable system. It actually has another name. This particular one is also called the periodic total lattice for SU2. By saying that, I just mean literally this this holomorphic symplectic manifold is the same as one that was studied in the literature on integrable systems and was called the periodic total lattice. Now, okay, so let me say just a few words now about this complex integrable system, and then that'll
Before
be
you go on, let me ask you, Andy, something.
Yeah.
When you say periodic Toda, I mean Toda has a size. I mean, this is the size of a matrix that you are supposed that describes the Toda. In other words, how many particles you have.
Yes.
What is the size in your picture?
Yeah, that's what I mean. SU2. So I think there's a periodic total lattice for every Lie group, right? And I mean the SU2 one.
Oh, okay, I see. Okay.
But indeed, we could have done this. So when I did, yeah, maybe I just should have said, maybe it would have been better to say periodic total lattice. Well, no, here I'm in the SU2 case. So this is the periodic total lattice associated to the group G equals SU2. Okay. But similarly, if I had done Yang-Mills theory from the beginning, starting with some other group, then I would have ended up with a very similar story in higher dimensions. And the complex integrable system that I would have ended up with is the periodic total lattice for that G.
Okay, I see. Okay.
Okay, so I think basically that, in the next talk, I'll try to explain some of how this complex integrable system shows up in the physics more explicitly than what I've said so far, and how we can use the physics to learn something new about this complex integrable system. Yeah, maybe that's a good place to stop. And then I can do maybe, if there's 1 or 2 questions, we can do them before I have to run.
Well, let's thank Andy for a great talk. And know that he has to leave in a couple of minutes. So we have time for just 1 or 2 quick questions, like you said. Feel free.
So connecting this to the first of the lectures that we heard, what's the so this gives us a singular elliptic vibration. What's like the Kodaira type of it?
Oh, yeah, these two fibers are, if I remember my Kodairaology correctly, these two fibers are both of type I1. It's like the simplest singularity that you can have.
Okay, thank you.
So it's literally the picture that I drew here. I mean, that picture looks like a cartoon, but even in the, so next time, one of the things we'll say is that this total space is actually equipped with a metric, even a hyperkähler metric. And relative to that hyperkähler metric, this is literally the picture that the torus actually kind of pinches itself off at one point.
But so this, of course, is the hyperkähler metric on the Hitchin system.
So this is an example of a Hitchin system. Right. That's right.
But you haven't said that yet. Okay, I don't want to steal any. I was just curious.
No, it's fine to say now. But the thing is that this Hitchin system, this is not the first one that you would think of when you think of Hitchin systems, because this is a Hitchin system on a sphere with 2 irregular singularities. So it's like a little bit exotic for, you know. It's in the world of Bicard and Bolch rather than the world of Hitchin or Simpson.
Right. And,
so in other words, this condition that the genus somewhere, the genus of a curve is greater than or equal to 2, here is violated. It's actually genus is 0, right?
That's right. That's right. And so of course,
1 maybe.
Yeah. No, it's 0. It's really it'll be these will be the spectral curves. They have genus 1, but the curve where the Higgs bundles live will be actually of genus 0.
Genus 0. Okay.
But it's the punctures make up for it. But
yeah, right. That's what drops the genus.
Right, but these are irregular punctures. Like, is there any? Maybe you said this. Is there any condition on what the orders of the poles can be, like, in relative to the rank that we're?
I think you can consider these things with arbitrarily bad irregular singularities, and you get those also correspond to some. Somewhat more exotic n equals 2 supersymmetric field theories.
Oh, very good.
Yeah.
Any other questions for Andy before he has to jet?
Do we have a minute, Andy?
Yeah, we have a minute.
Yeah, I have a minute. So now this is very, very, very basic. It just a reflection of my confusion. From the point of view, let's say, of people who are studying individual integrable systems, is studying the dynamics of an individual integrable system like moving along a fiber?
Yes.
Because when you say that this is an integrable system as a whole, in fact, on every fiber, since you have a torus there, I'm presuming that this is a little bit like a Jacobi torus when things are linearized. And basically, when you are studying a dynamics for a fixed integrable system, you are actually moving along that fiber, correct?
Right. Well, these are like it's like the action angle variables, right? You have
correct. That's what I'm saying. So when people study integrable systems, they're studying individual fibers in some sense of this picture, correct?
Well, isn't it? I mean, I think when people talk about the Toda integrable system, I thought they're talking about the total space of this family. I mean, it's true that the dynamics, you know, with any particular initial condition, the dynamics kind of live on a single fiber, but
how do you move? You see, that's the whole point. You know, how do you move from one fiber to another fiber using dynamics? I don't think you can do it.
No, that's right. That's right. The Hamiltonians of the theory will not move you from one fiber to another. That's right.
Okay.
Okay. Yeah. I better run.
Yeah, thank you.
Thanks. See you.
Yeah. Thanks, Andy. Bye.